All right, let's look at some properties of vectors in R2. So we take, this is Theorem 4.1 of your book, in section 4.1, of course. So take U, V, and W be vectors in the plane. So in the plane means R2. So I'm going to take that out. I'm going to make sure everybody understands. These are vectors in R2. That means the vectors have two dimensions, the two components. And we have C and D scalars. So let's see, these are very important properties to look at because in the next section we're going to generalize and these are going to be part of the definition of a vector field. So we need to pay attention closely to what they say. So if you add two vectors with the standard definition of vector addition, that means we add them component-wise like we just saw, then the resulting vector, the sum, is going to be also in R2. It's not wrong to say in the plane, but for the purpose of generalizing next to Rn, this is R2. Okay, so this property is very, very important, and as we're gonna see soon. This is called the closure property under addition. And so when you add two vectors in a set, you get a vector that's in the same set. That's important. Now, this you might recognize from section 2.1 when we learned about matrix addition. U plus V is V plus U, so that's the commutative property of addition. This is the associative property of addition. Now, this is new, the additive identity property. So when you add 0 here, represents, since we are in R2, the vector 0 represents this ordered pair 0, 0. So if you add 0, 0 to a vector, it makes sense, you add them component-wise and you get U. Now, negative U, we said it is the additive inverse. So if you add a vector and its additive inverse, you should get the 0 vector. So we take these things for granted because that's how the geometry that we've learned so far works. Now, the next properties have to do with scalar multiplication. So if you multiply a vector by a scalar, then you land in the same set that you started with. So again, we said that this is the same as saying R2. So we say that R2 is closed under scalar multiplication, or under the scalar multiplication, the standard scalar multiplication that we just defined. Alright, so here we know this from matrices. You can distribute a scalar to the sum of two matrices, in our case, two vectors in R2. And here we can distribute the vector to two scalars. And we can multiply, if we have to multiply by two constants, it doesn't matter the order in which we multiply. And finally, this is going to be very important in vector spaces. If you multiply a vector by the multiplicative identity, then you get back the vector. So let's see, for who would be the multiplicative identity in this case? So we have not defined any other type of multiplication other than scalar multiplications. In our case, this 1, is it a vector or is it a scalar? So let's look at it. U is a vector, so we're going to call that U1, U2. So what do I multiply U1, U2 by to get U1, U2? I only know one kind of multiplication. I only know scalar multiplication. So this guy must be the scalar, that's 1. Right? So 1 times that. It seems very trivial, but once we define addition and scalar multiplication differently, then it's not going to be so trivial anymore. Okay, so how do we prove these properties? So I'm going to just point out, so these properties are easier to prove than the ones for matrices because these are vectors in R2, so there's not a lot of work to do here. So the book does the proof of 3, and we're going to look at it briefly Those of you who've had Calc 3 have seen this in Calc 3 with 3 dimensions. So you take 3 vectors, u, v, and w, in R2. That means each one of them has 2 components. So you're going to write u as u1, u2, v as v1, v2, and w as w1, w2. Now in the case of matrices, we wrote these guys as aij plus bij plus Cij. So this is the same exact property that we're proving, but it's a more specialized case, because now instead of having m times n entries in each one of these arrays, we only have 2 entries in each array, so it's easier. Okay, so but the principle is the same. We revert back to, we try to use properties of real numbers in order to prove these properties of vectors in R2. So what we do is we add parentheses first, just like in algebra. So we're going to add component-wise the vectors in the parentheses, and then we're going to bring in our w1, w2 vector. So how does this work? So we have our v1, u1, v1 up here. So to this guy, we're going to add the component w1. So here's u1 plus v1, and I'm adding to it the component w1. Next, I look at the component u2 plus v2, and to it, so this is another component, right? So to this component, I'm going to add the w2 component. Okay, so now I have all real numbers in each component. So u1, v1, w1, u2, v2, w2 are all real numbers. So at this point, with matrices, we say by the associative property of real numbers, we can switch the parentheses around, and we can now put parentheses around v1 plus w1. Okay, so from here on, so this is where we used the associative property of real numbers, which we're allowed to assume. Okay, so now we're going to go back and apply the definition of vector addition in reverse. That means we're going to take apart this vector. So this is one vector with one component and then another component, right? So we're going to split this vector apart. You see that you can pull apart u1, u2, so that's what happened here. And then the remaining components there gets grouped together into another vector. Okay, so there's u1, u2, and now this gets split in its turn into 2 vectors. And now we can rewrite vector u, vector v, and vector w in terms of their, generally